The Honorably Committee of International Conference on Learning and Development, ICLAD 2021, with the conference theme is Towards Energy Transition, Harmonizing with the New Form, which is now conducted virtually. I'm so glad to be here to present my paper to you all. Up to 15 minutes ahead, I'd like to explain to you about my paper of optimization of capacitor placement on medium voltage 20 kV in PLN area Binjai feeder BG02. First of all, I'd like to introduce myself. I am Teguh Zajerah Siregar, 27 years old. I work in Electricity Company of Indonesia, headquartered in Sumatra, which is called P3B Sumatra. I'm in Planning Division, on duty to evaluate and create any plans to strengthen the electricity system in Sumatra especially. Now, talking about my paper, it relates to the correction of voltage drop in the grid. There are many ways to overcome voltage drop issues as follows. Grid reconfiguration. The second, build a power source, for example power plant. And the third, integrating capacitor bank to the grid. I'm going to talk about the capacitor, how it works, and the function of capacitor. The capacitor is basically a simple device. This tool consists of two plates separated by an insulating material between the two plates. When the capacitor is given a certain voltage, then each conductor plate will have the same charge, but opposite types. When the capacitor terminals are connected with an alternating current source or network, it will produce a current that is leading to the voltage and is commonly called a capacitive current. I used the application of ATAP 1260 or ATAP 1260 to calculate and measure the optimum placement and the capacity of the bank used in the grid. Before I come to the explanation of voltage drop, I'd like to start from the definition of losses, because it is too much related to the voltage drop. In the process of transmission and distribution of electric power, considerable power losses are often obtained due to losses in the line and also losses in the transformer used. The two types of power losses have a great influence on the quality of the power, as well as the voltage delivered to the customer side. Voltage values that exceed the tolerance limit will cause non-optimal work of electrical equipment on the consumer side. In addition, large power losses will cause financial losses on the side of the electricity management company. The following is an explanation of the losses that occur in the distribution network. The simulation is carried out in three stages. Namely, the initial stage is calculating the initial condition of the power flow in the feeder using the Newton-Raphson method through the ATAP 1260. Then conducting a capacitor optimization study with the optimum capacitor placement tool in this application to determine the optimal location and value. The value of the capacitor to be injected into the feeder. After that, perform the calculation of the power flow again after the shunt capacitor was injected according to the location and value obtained through previous optimization studies. Capacitor here is used to increase the voltage level in 20 kV at Binjai feeder, which occurs the voltage drop there before the installment. It means a little bit harmful for the system, especially for the customer. Then the question is, how could the capacitor bank increase the voltage level of the grid? In this paper, I provide 7 banks of capacitor. Each generates 200 kVAr. The capacity of the bank is calculated through the formula stated in this paper. The principle of this capacitor works is about the power triangle. Maybe you all know about the power triangle. I'm gonna explain first about the power triangle. There are 3 parameters that we should find in the power triangle. The first, reactive power, and the second, active power, and the third, apparent power. The capacitor that will be used to increase the power factor is installed in parallel with the load circuit. When the circuit is given a voltage, then electrons will flow into the capacitor. When the capacitor is full of electrons, the voltage will change. Then the electrons will come out of the capacitor and flow into the circuit that needs it so much. At the time, the capacitor generates reactive power. When the change voltage returns to normal or fixed, then the capacitor will store electrons again. When the capacitor discharges electrons, the same means that the capacitor supplies reactive power to the load. Because the load is inductive, while the reactive power is capacitor. As a result, the reactive power applied becomes small. Capacitor banks are used to improve the quality of electrical energy supply on the load side. Among others, improve voltage quality, improve power factor, and reduce electricity distribution losses. The capacitor bank generates the reactive powers needed by system. Because commonly, our system consumes reactive power at most, higher than active power. So, by generating reactive power, it means that the bank compensates the reactive power of the load. The more little reactive power generated in our grid for the inductive load, the voltage level in the system will be increased because the more little losses occurs in the grid. By placing the capacitor in the medium voltage, it is expected that the reactive power could be reduced and the loss of power in the network is also reduced. Regarding the optimum placement, we talk about how to measure the optimum place, where we should attempt to put on the capacitor on the grid. The optimum placement is based on the most critical voltage and the highest losses found on the grid. That's the point. In radial configuration, the point of critical voltage should be next to the end of the grid line. We should find the least voltage level there. We used this application, and through this app, we could simulate and find the most critical voltage bus and the highest losses on the grid. Then we could find the optimum placement. As in this paper, through this application, we could see that the minimum voltage is on the BG02 feeder, and it's almost next to the end of the line, around 80% of the total grid length. Loss of network power decreased by 15.6% for active power and decreased by 19.3% for reactive power, and increased power factor of network to 0.907 from previous 0.822, and from the result it fits to the grid code for the maximum voltage drop of 10%. So, through this paper, I'd like to explain to you that there are many ways to overcome the voltage drop, especially in this distribution network or grid. But I suggest to you in this paper that we should choose the capacitor placement because it is rather cheaper than the grid reconfiguration and even or the power plant building that is so expensive. Through this paper, by my explanation, we could know that how to measure the optimum placement of the capacitor through this application. But I suggest to you that if your configuration of the grid is not radial, do not think that the optimum placement is in the end of the line, because it's totally different. In my paper, it is radial network. So we could easily find where we should place the capacitor. But in the spindle configuration or any configuration others, it's totally different. Do not even think that it's just the same. No, it's totally different. And then as the closing statement, I would like to deliver 1,000 thanks to the ICLAD committee for this chance to present my paper. I know my paper is just simple, but it's very, very useful for the customer, because especially for me, I work in the electricity company of Indonesia. My concern and my company concern is how to make our customer satisfied. So if you talk about satisfying the consumer, we should provide the best voltage level, almost zero voltage drop for the grid and for the customer, because the better our grid, the better the voltage drop of our grid. No voltage drop, almost zero voltage drop, it means that the power generated by the generator is almost the same with the power we or the customer received. That's the point of the losses. It means almost zero losses. And that is the purpose of this paper, to make almost zero losses. Even though it is impossible to make zero, at least almost zero. And for the closing, thanks a lot for the great attention. Hopefully, it could be useful as our reference to empower and strengthen the electricity system in our grid. Thank you.